Okay, can you see that?
Yes, we can see this.
Very
All
good.
right.
Let me see.
So we are happy to have Gonzalo Villa uh, speak about gravitational waves from high temperature strings. All right, Gonzalo, please take it away.
Okay, thanks. Well, let me begin by thanking the organizers for, giving me the opportunity to give this talk, and also for keeping the String Pheno seminars well and alive. That is, I'm very deeply, yes, I really like these seminars. I'm very happy they're still going on. And today I want to tell you about this work that belongs to a long collaboration, a big collaboration. Well, can you see this? The Zoom? Yes. Okay, I think I got rid of it. Okay, so this is work I've done with my collaborators Andrew Ratul, Anshoma Francesco, and Fernando. And it regards gravitational waves from a gas of thermal strings in the early universe. So this talk is, well, the work is divided into two parts at the moment. In the first paper, we describe the kinetic theory for a gas of strings, and I will not have too much to tell you about on this topic today. Just the basics, just enough content that is needed in order to understand the topic of the second paper, which is the gravitational wave part. So what happens when you put this system, this gas of thermal strings, in cosmology, and what are the sort of computations you have to do in order to find the gravitational wave spectrum. So before starting though, I would like to give you a little bit of motivation on why gravitational waves. And to motivate it, I would like to make a statement that we are all very familiar with, right? Which is the fact that gravity is weak. Now, one of the implications of this is that then it's very hard to reach energies that can test the quantum gravitational field in the laboratory. And so it would seem like we're out of business. But this is not the only implication that gravity is weak. Indeed, if gravity is weak, then gravitational waves interact very weakly, and in particular, the universe is always transparent to them. And so these waves carry interesting information about whatever was the physics that sourced them. And I believe this is food for thought. And so this talk is going to be divided into three parts. In the first one, I motivate a little bit more gravitational waves and why I believe they are a good test of high energy physics and the physics of the very early universe. Then in the second part, I will tell you about this Hagedorn phase, how we put up this kinetic theory for highly excited strings. And then in the third part, I will put this gas of strings in cosmology and tell you what are some consistency conditions that we have to check and so on, and how to compute the gravitational wave spectrum. So the idea is very simple. The early universe is very energetic, and so high energy process will source high frequency gravitational waves. And this very simple observation is actually attracting a lot of attention. So there's this white paper here involving both theorists and experimentalists. So, this is not a crazy theorist idea. And actually, very recently, I knew of this last week, the collaboration GravNet was recently awarded an ERC synergy grant to do gravitational wave searches around the gigahertz. So, this is very interesting. This is actually happening. It is true that the sensitivities that they have are not enough in order to prove these cosmological backgrounds of gravitational waves that I want to tell you about today. And also, there are some subtleties regarding the type of spectra that these experiments can prove. But nevertheless, this is the first step. This is a step forward, and our job as theorists is to explore the possibilities and opportunities that these backgrounds provide. So let me give you an example of such a background, and it is a standard model. So we know that in the early universe, the standard model was a thermal plasma, right? And it turns out that thermal plasma source gravitational waves. This is very obvious at long wavelengths where hydrodynamic fluctuations induce currents, right? Induce gradients of energy and momentum, and this sources gravitational waves. And then in the high frequency side, what you are fine-grained, you have to study quantum field theory, and then the linear coupling to gravity sources, the plasma will source gravitons due to this coupling in this manner. Now you can sit down and compute, and people have done it, and this is what you get. So what I'm showing you here is the energy density in gravitational waves per logarithmic frequency interval. That is what we call the gravitational wave spectrum. And is the amount of gravitational waves that are emitted per E-fold. Now, on the right-hand side, I have a production term. And what I'm seeing here is that, the thermal bath is sourcing a fraction of its energy density into gravitational waves. Then there is a function related to the emission rate, which depends on, it's a ratio of the two scales on the problem, the frequency of the graviton and the temperature of the plasma, and picks whenever its argument is order 1. And then there is the gravitational coupling, essentially. This is a gravitational process, and so, the fraction of gravitational waves is suppressed by temperature over M Planck. Now, what is particularly interesting about this is that this product, rho times a to the 4, is constant whenever the bath sourcing gravitational waves behaves like radiation. The argument of this function here is also constant because, the frequency and the temperature redshift in the same way, modulo high energy degrees of freedom, which don't change the conclusions qualitatively. And so the only the only time dependence in this equation arises in this ratio here, T over M Planck, which is the largest at earlier times. And this is an example of an UV sensitive quantity in the following sense. The largest contribution to the gravitational wave spectrum today comes from the very earliest times. So, the signal is carrying a snapshot of whatever the universe looked like right after reheating. And I find this very interesting, very remarkable, and it's definitely worth exploring. A natural question to ask is whether, what happens if you have new physics at the time of reheating. And we checked in this article that it is very hard to get a larger amplitude. It's hard to get a signal that is stronger than that predicted from the standard model at a given reheating temperature within field theory. And the point, or one of the points I want to make today is that stringy effects instead give a larger signal, which is something we're not really used to. Typically, high energy effects decouple. And this is a counterexample of this. And so it's really an opportunity. So, in case you want to fall asleep, let me show you the results first. So what I'm showing here is the appropriately normalized energy density in gravitational waves emitted by this Hagedorn phase, or this gas of thermal strings, against the same thing for the standard model, where I am equating the reheating temperature with a string scale. And so, there are a couple of things that you should notice. One of them is that the frequency is fixed, essentially. And the reason is this ratio frequency over temperature that correlates the frequency of the gravitons today with the energy with the temperature of the CMB. And so it's, in standard cosmology, it's hard to change. And what we find is that, as I was saying before, the amplitude is larger for the string gas under the same conditions, which is something very interesting. And this is linear in the reheating temperature for the reasons I was explaining before, right? The contribution is linear in temperature. Okay, so if there are not any questions on that, then let's move to the second part. I want to describe a little bit what is the kinetic theory. What are the ingredients one needs in order to do this computation? So the idea is the following. Let me forget about inflation for a moment. I will have a couple words on that before, but for the moment, let me just extrapolate back the hot Big Bang. As we go back and back in time, then the energy is involved in the universe are larger and larger. And then if our universe is described by string theory, then at some point you hit the string scale. The temperatures hit the string scale. And then the systems enter a Hagedorn phase. So in this Hagedorn phase, the thermodynamics gets funny, and the reason is this exponential here. So the density of states grows exponentially. And if you remember your thermodynamics, then equilibrium distributions are something like density of states times Boltzmann suppression. And then these two exponentials, this exponential and the Boltzmann suppression will compete. What happens then is that as you pump energy into the system, you don't raise the energy. Instead, this energy is used to excite this exponential number of states, so these oscillator modes. And so what happens is that the strings become long. Now, the equilibrium thermodynamics of this system is well understood, but we have to do a little bit better if we want to do cosmology. And, as I was saying before, the exponentials compete and they generate a new scale in the problem, which is given by the inverse temperature difference. It turns out that this length big L, it turns out it's the length of the typical string. It's the typical length of the strings in the ensemble. Now, the reason why I'm saying that it is not enough to know the equilibrium distributions and the equilibrium physics is that in cosmology, always an expanding universe tends to pull systems out of equilibrium. And so the best you can do is to have equilibrium as an approximate notion. And this is controlled. This is a good description of the system is if the equilibration rates are much faster than Hubble. And so we need this ratio to be much larger than 1. So the name of the game, if we want to describe this gas and describe it as a gas in thermal equilibrium, is to compute these equilibration rates. The way that we did it is as follows. We compute decay and absorption rates in a manner I will explain you in a moment. Then with this at hand, we can formulate Boltzmann equations, find equilibrium solutions, and then perturb these equilibrium solutions to study how the system tends to come back to equilibrium, which gives information about the equilibration rate. Now, I will not have a lot of time to tell you about this here, but you can check the paper, the first paper, and also a previous seminar I gave in this seminar series, which is in YouTube, I believe. Today, I'm just going to tell you what are the key ingredients you need in order to compute this decay and absorption rates. And the idea is the following. In principle, this is actually very, very hard to compute because, the vertex operator of highly excited strings are typically very complicated. And on top of that, you will need to compute an exponentially large number of interaction rates in order to pose the Boltzmann equations. What we're going to do instead is to adopt a more coarse-grained point of view and study typical strings at fixed level. So, what I'm going to do is to fix the energy of the string. And then within that energy, so within that level, average over all the possible configurations, which, is reminiscent of what we always do in thermodynamics. So let me give you an example. Let me study the average semi-inclusive decay rate for this process here, for which a long string of length n decays into a pair of strings at levels n1 and n2. And I'm going to assume for technical reasons that I know the vertex operator, so I know the particular structure of one of them. Then the type of amplitude I need to compute is the following. I sum over all final states which I ignore at a given level. I average over all initial states that I ignore at a given level, and this curly G here is the number of states at the level n. And then the name of the game is to compute this quantity here. Now the trick, initiated I believe by Amati and Russo, is to trade these sums by a trace by inserting projectors. And if you do that, all you need to do is to compute the trace of this particular operator for a given vertex operator. And traces, at least in string theory and flat backgrounds, are things we know how to compute. And indeed, Mañas did it. And it turns out that, after the dust settles, he did it in a toroidal background. The decay rates have simple expressions. In particular, at leading order, when I'm taking n1 and n2 and n to be very large, so I'm studying highly excited strings, It turns out that the result is independent of what is this vertex operator V1 that I was showing, which is, and then I can, the results just admit a random walk interpretation as follows. The case for the decay of an open string, here what I'm showing is a string of length big L decaying into this pair of strings of length little l and big L minus little l. It turns out that this is independent of either length, either of the mother or of the daughter strings. What this computation is done assuming you have a space-time filling brain, and what the sort of semi-classical interpretation that you should have in mind is that the brain can chop the string off at any of its points with equal probability. Now the case of the closed string is more complicated. What we have is, again, the same process. I have a closed string of length L, length big L, it breaks into a pair. And the emission rate is as follows. It's proportional to G string squared, and unsurprisingly, it's proportional to the length of the mother string, because this process can occur through any of its points. And then there is this geometric probability, which is a probability that a closed random walk of length L in d dimensions self-intersects. And this number D is actually very important for the thermodynamics. So let me give you a couple comments on what is intuition behind it. In the toroidal setup, it appears it is a number of dimensions along which the strings cannot wind. And so it's a number of dimensions which have radius much larger than the length of the mother string. One can generalize this idea just by, this gives you a clear and neat separation between which dimensions are large and which dimensions are small. And in the small directions, the string is, if you want, already self-intersecting. And so I only need to take care about the other ones. And this, as we will see later, is important. Now, so let me just quickly recap. The thermodynamics is then fixed by whatever is the number distribution of strings, whatever is this number of effectively large dimensions D, and the inverse temperature difference, which is this 1 over L I was talking about. And it turns out you can fix all of this. Now, if your system is in equilibrium, then the number distribution is fixed, or in approximate equilibrium. The temperature difference can be tracked very easily in cosmology through conservation of entropy. So, once you have an initial condition, you are fixing 1 over L at any time. And lastly, it turns out that the number D is fixed generically in realistic setups. And the intuition behind this claim is that, realistic ingredients like branes and fluxes, they have energy, they curve the extra dimensions, and localize the highly excited strings within a very small box in the extra dimensions. The size of this box is typically much smaller than this L here, so than the size of the typical string. And so the thermodynamics is effectively 3 + 1 dimensionals. And with this, we have all the ingredients we need in order to put the system in cosmology and study the gravitational wave spectrum. But first, I want to make a couple comments on consistency, because all of this might sound funny to you, because we're studying large energy densities, right, of order 1 Ising units, if you want. So you might be concerned that the 4-dimensional description doesn't quite work. The issue here, though, is that 4-dimensional general relativity is a good approximation and receives corrections in powers of h over mkk, right? This ratio of curvatures. If you have stringy energy densities, and h squared is around this quantity here, I'm string to the 4 over m Planck squared. And so the ratio of Hubble with respect to the kk scale is given by this quantity here, which is typically small. If you are to have control under your effective field theory already from the beginning. In particular, let me take the simple case in which I have just one large force cycle, ignore all warping and so on, then the ratio looks like this G string over tau. both, G string is a small quantity, tau is the volume of the Ford cycle, which I assume to be large, and so this is typically small. So the four-dimensional setup should be a good description of whatever is going on. Another comment I want to make in this note is, what is a possible embedding of this? And brain anti-brain inflation is a very good candidate. The reason is that, in brain anti-brain inflation, the energy density of the vacuum is around twice the tension of a D3 brain. And then when inflation ends by brain anti-brain annihilation, this energy goes to highly excited strings, and provided certain decay channels are open, this will thermalize. And so will give rise to a Hagedorn phase. It is worth noting, though, that, the computation of the gravitational wave spectrum is largely independent of whatever source the Hagedorn phase, which I think is important to notice, but it's important also to have an idea of how this could have been rise to. Now, let me just give you some quick facts. It turns out that the thermodynamics is dominated by highly excited open string degrees of freedom, and it's important that there are open strings in the game. And if you check the Boltzmann equations and play with them a little bit, you will find that, of course, this energy density back reacts and sources the expansion of the universe. That gives you Hubble in terms of the equilibrium distribution. And then this open string reach thermal equilibrium, which, as I was saying before, is not obvious. And actually, if you have only closed strings, it is harder. The equilibration rates and Hubble are parametrically similar. But with open strings, the story is fine, and you can see that there is thermal equilibrium. Now, as the standard model did, this source gravitons in out of equilibrium processes. And then as the universe expands and the energy density is diluted away, they just decay. These highly excited strings simply decay into standard model degrees of freedom. So they give you a natural reheating. Today, I want to focus on how they source out of equilibrium gravitons. And the sort of computation you have to do is similar to what we were doing before. You have a highly excited string, and it decays into another highly excited string and a graviton. I want to compute this average semi-inclusive rate. In this case, I do know what is the vertex operator in the game. It's the vertex operator of the 4D graviton. And then you can, again, play the same trick, exchange this for a trace, and do the computation. Now, if the worldsheet CFT factorizes, which, within the usual approximations like dilute flux and so on, is true at leading order, you can do this computation because the graviton vertex operator, the 4D graviton vertex operator, only acts non-trivially on the external part of the CFT, which is the free part. And so one can sit down and compute. And because of this average, whatever is going on in internal dimensions drops out at leading order, which is interesting. It's largely model independent. After that settles, one can do the computation and gets this result here. The emission rates of graviton from a mother string of length little l is, of course, suppressed by m string over m Planck, and there is some function. This is a gray body. This is a gray body spectrum, but for the current purposes, it's just some function that correlates the frequency of the gravitons with the Hagedorn temperature, so with the string scale. Once we have this, it's very simple. It's very easy to compute the gravitational wave spectrum. You just have the standard redshift of the energy density in gravitational waves plus a production term, which is given by, this constant production of gravitons out of the bath. And what we find is something very similar to what was happening for the standard model. So we have the energy density of the bath sourcing a fraction of its energy density into gravitational waves. There is some function that correlates the frequency of the gravitons with the Hagedorn temperature, and the process is suppressed by the characteristic scale of the problem over m Planck. In this case, the scale is m string. And so one can sit down and compute. I'm using a parameter x here, which parameterizes deviations from standard cosmology after the Hagedorn phase. If you set x equals 1, I am assuming a standard cosmology. And then what you find is that this normalized energy density for M string of order 10 to the 15 GeV, so around 10 to the minus 4 M Planck, is near 10 to the minus 6, which is essentially the VPM bounds. Okay, technically you have to integrate this in log omega 0, but this is a ballpark. The spectrum is quite peaked. Again,
just to let you are
yes?
25 minutes in, just to let you know.
Yes. I have 1 minute left. Thank you.
Right.
So this is the spectrum. Yeah, this is the spectrum for the Hagedorn phase against the standard model. And as we were saying before, the frequency is fixed. If you assume standard cosmology after this Hagedorn phase, it is linear, grows linearly with M string, and it's larger than the standard model. And with this, I conclude. Let me just, a quick summary. We've described string thermodynamics in terms of these typical strings, right, with coarse grain over the levels. This allowed us to compute equilibrium solution and equilibration rates, which are important if you want to put this in cosmology. We've seen that, typical ingredients in string compactifications render universal thermodynamics. So this is very little model independent as long as you have this gas of thermal strings in the early universe. And again, graviton emission under usual assumptions is largely model independent. Now, it would be nice to study more implications of this Hagedorn phase. We can also source closed string moduli and also and more particles that are massless from the worldsheet point of view, but then IR effects give them a mass, so they could be candidates for dark matter and so on. But I just hope the main point is clear, which is that gravitational waves at high frequency provide a very good opportunity for us high energy theorists to test high energy physics. And with this, I conclude. Thank you very much.
All right. Thank you, Gonzalo, for the nice talk. Do we have any questions from the audience? If so, please speak up. We can also have some time after for non-recorded questions. All right, so let's thank again Gonzalo and Nacho for their nice talks.
Thank you.
And we will have another seminar meeting in the future. All right, so we will go now to the non-recorded post-talk discussion.